Okay, welcome to the next lecture on voltage stability. In the last lecture, we have studied QV sensitivity analysis, which is one of the methods for static analysis of voltage stability. Now, as the second part, we move on to QV modal analysis. QV modal analysis. Before moving on to the concept of QV modal analysis, we will just have a recap on the concepts of eigenvectors and eigenvalues, which we have studied in the first lecture. In linear, an eigenvector or a character of a linear transformation is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. What is a linear transformation? Let T be the linear transformation on the vector V. Okay, so this linear transformation will give out a scalar into that vector V. So after the linear transformation, the vector is either stretched. If lambda is positive, then the vector is stretched, right? This was the vector lambda. Lambda V will look like this. It will be stretched without changing the direction. Okay, now if lambda is negative, what happens is the stretching happens in the opposite direction, which means this is the initial vector, right? If the stretching happens in this direction, then the resultant vector will be small, right? So this is lambda V when lambda is positive. This is lambda V when lambda is negative. Okay, so this transformation can be of different types. This T of V, T is the transformation here. This can be of different types. It can take different forms. Mapping vectors in a variety of vector spaces. We can map vectors in a variety of vector spaces. Suppose this happens in a vector space capital V. Okay, so the mapping happens to itself. I mean the same vector space. It is mapped to the same vector space, suppose. Then the eigenvectors can also, if the mapping happens to different vector spaces, then the eigenvectors can take many forms. For example, the linear transformation could be a differential operator. If it's a differential operator, then it will look like d by dx. Then T is d by dx. Okay, so d by dx of e raised to lambda x equals lambda e raised to lambda x. So this is the linear transformation. Again, some scaling up or scaling down has happened by a scalar factor lambda. Okay. Alternatively, the linear transformation could take the form of an n by n matrix pre-multiplied to the vector. So T of V can be of this form also, A into V, where A is an n by n matrix. In that case, the eigenvectors are n by 1 matrices or n by 1 vectors. And if the linear transformation is expressed in the form of n by n matrix A, then the eigenvalue equation for a linear transformation can be written as AV equals lambda V, which we have seen in the form of AX equals lambda X in our lecture 1. Now, what about the importance of this in modal decomposition?